Look at the traffic grid of a major city. To predict how cars move, engineers often translate physical systems into the language of circuits. In this model, the volume of traffic acts like current, the width of the road serves as resistance, and the pressure of the commute functions as voltage. By representing these systems as electrical equivalents, we can use the same laws of physics to analyze a hydraulic pump or a weather pattern. To navigate these models, we must first learn to categorize the building blocks that make them up. Every element in a circuit is either active or passive. Active elements, such as batteries or generators, possess their own energy and push it outward into the system. Passive elements do not have their own energy, they simply receive it. These passive elements process energy in three distinct ways. A resistor consumes energy and releases it as heat. An inductor stores it within a magnetic field, and a capacitor stores it inside an electric field. This diagram shows a more complex active component called a dependent source. Notice the diamond-shaped symbols. These indicate that the output of this source is strictly controlled by a voltage or current measured somewhere else in the circuit. We also distinguish between ideal and practical sources. In the real world, every power source has internal resistance, labeled here as Rint. This means the voltage received at the terminals is slightly lower than what the source produces. In a DC circuit, electrons move uniformly in one direction. However, when we apply an alternating sinusoidal supply to inductors and capacitors, we encounter reactance. This creates a form of inertia that causes a time delay between the voltage and the resulting current. Because of this delay, the voltage and current waves drift out of sync. To track which one is ahead, engineers use a specific mnemonic, ELI, the Iceman. Let's look at ELI first. In an inductor, represented by the letter L, the voltage, denoted by E, leads the current, I, by exactly 90 degrees. For IC, the relationship flips. In a capacitor, the letter C, the current, I, leads the voltage, E, by 90 degrees. This means the inductor and the capacitor pull the timing of the circuit in opposite directions. This diagram shows a series RLC problem with specific values. We have a 12-ohm resistor, a 0.15 Henry inductor, and a 100 microfarad capacitor, all driven by a 100-volt, 50 Hz AC supply. To solve this, we must first convert the physical inductor and capacitor values into ohms. Using the formulas at the bottom of the page, we calculate the inductive and capacitive reactance based on our 50 Hz frequency. This results in 47.13 ohms of inductive reactance and 31.83 ohms of capacitive reactance. Now look at the impedance formula. Because the timing of these components is out of sync, we cannot simply add these ohms together. Instead, we use this vector formula to find the total opposition to the current, known as impedance, or Z. By taking the square root of the resistance squared plus the difference in reactances squared, the total impedance calculates to 19.4 ohms. Here is a quick check. If our total impedance Z is 19.4 ohms and our supply voltage is 100 volts, use Ohm's law to calculate the total circuit current. Dividing 100 volts by 19.4 ohms gives us a total circuit current of 5.14 amps. This specific value allows us to determine the exact energy distribution across the rest of the branch. These calculations show the next step, multiplying our 5.14 amp current by each component's resistance or reactance to find the voltage drops. Look at the inductor's voltage, 242.2 volts, more than double our 100-volt source. This becomes clear on the phasor diagram. Because these voltages are out of phase, their vectors point in opposite directions. Functionally, they subtract from each other. We calculate the exact phase difference using the power factor. Dividing resistance by total impedance gives a 51.8-degree lagging angle. The gray vector triangle proves the final result. Combining the opposing inductor and capacitor vectors exactly matches our original 100-volt source. To solve any AC circuit, categorize your active and passive elements. Use Eli, the Iceman, to track the phase shifts, and apply vector math to find your total impedance.